Okay, we'll record notes in one video and then two examples in another, try to kind of break that up, and then we'll turn people loose if you want to do homework um, or work on labs or whatever. This chapter 4, finally we have the famous Newton's laws. Okay, Newton's laws of motion. This is, so whether we had an easy problem or a really easy problem, judging by your test scores, is whether or not there was any acceleration. Okay, that's what we've been learning so far these first two chapters. How do we treat different accelerations? How does that affect motion? Newton's laws is what causes acceleration. Okay, so the first law should be called Galileo's law. And they figured this out by looking at astronomical objects. The moon of Earth. Galileo had a good enough telescope, he could see the moons of Jupiter. And so Aristotle was the previous philosophical big shot. He said, well, everything that I start moving, I could annoyingly throw a projectile, but you know what happened. Everything eventually comes to a stop. Duh. Try to move something, and it'll stop. So that's what naturally is supposed to happen. But Galileo said, oh, no, wait. The moon and those other planets, those are things. And they move around up there in uniform motion. They just keep going. The moon comes by every 28 days. It goes through its phases. It never changes. It never stops. It's been there as long as people have been looking up. Much, much longer, in fact. Um, so, no, the state of the universe must be uniform motion, and we're all stuck to this Earth, and it does keep going around and around the sun. And we just make minor little changes as we bump into each other. Okay, so they said it was it was a big deal back then. The real first law of motion is that things continue at rest or in uniform motion at constant speed, hey, unless acted upon by a non-zero net force. So we are saying, where does acceleration come from? In our notation so far, what would you say motion in a straight line at constant speed? If we're in this, a straight line means it can't turn. So if we're in the same direction at constant speed, we're just saying what? Maybe. Velocity is constant? Or you could say the change in velocity is zero, and therefore your acceleration must also be zero. Well, okay, so the natural state of stuff is to not accelerate. But if I have a non-zero net force, whatever that means, then it can accelerate. Okay? And it's a really simple logical solution. If I hold the ball in my hand, it just stays there. It doesn't move. It doesn't accelerate up or down. But if I remove my hand, it starts accelerating down. And why was that? Well, okay, and then so there's gravity on it. There's gravity on everything. Why was it not able to accelerate down before? Yeah, I'm supporting it. We call that a support force or a normal force. And so those forces are balancing out, allowing it to not accelerate. Okay, so it's really a special circumstance. And we don't accelerate down because the earth, the floor, there's a solid underneath us, supporting us. Okay. Mass, can you see this? Oh no. That's not going to let me do that. So this should be a little bit mysterious. It says every object, each body, they would say, has mass, and it's the measure of the quantity of matter. Oh, that's actually not true, but it's close enough for chemistry and for high school physics. We measure mass in kilograms. In kgs, that's important, kilos. Okay, and force in newtons. We'll just use capital F for force in newtons. And we'll explain how those two relate to each other really fast. The property of inertia. If you sanitized your hands, or if you promise to, I can demonstrate that